our next talk is by Laura. Laura or Jane. She's from San Francisco. She works at IBM Aspera. She was in India for a week, so she has been eating all the Indian food. And she told me in the morning that she has tried almost everything. Then I told her that now you're in Pune. You are definitely not tried everything. So I want to give all of you a food challenge that you will tell Laura one dish that she hasn't tried it, and then you will take her to that place and let her try it, and we'll see what happens. Okay? Is anybody up for that challenge? I cannot hear you again, but it's okay. We'll see. So Laura is going to talk about how they build their analytics tool at IBM Aspera, and I think she's just getting ready.
Thanks, Pratmesh. Yeah, so I'm excited to be here in Pune, and thank you all for coming to the conference today. As mentioned, I work at IBM Aspera. I'm a full-stack software engineer there at just like we were talking earlier, big company, but I get to work on all parts of the stack. So I'm going to tell you a little bit today about how we turned a lot of data into something that was more understandable for our users. So at IBM Aspera, we do high-speed data transfer. Companies like Netflix, Disney, JP Morgan, they use our software to transfer large amounts of data from one place to another. Recently, Fox Sports used Aspera services to live stream the Women's World Cup. In the past, similar data speeds have been achieved through using things like satellite technology. But with Aspera, we have a proprietary HTTP protocol that allows us to transfer more data faster and more securely. So while we transfer data, for every second that a transfer is in progress, we record statistics about the transfer of data. So if we wanted to create an analytics platform showing users how their transfers are doing based on the statistics that are recorded every millisecond, that's a lot of data. So we had some challenges. We had big data, and then we needed to store it somewhere that would be quickly accessible, and we had to display it in a way that looked better than a log file. So we have a daemon that's generating massive amounts of data. What we were doing initially was writing our data to a log file. We used Ruby to parse that log file and then rewrite it to a brand new log file. This was really inefficient. It would take several minutes just to get information around one transfer. We had a batch job that we would start when we needed the data to begin the Ruby script. And so at this point, we've already processed the data twice. We've written it from the daemon to the log file, used Ruby to reprocess the data, and write it to a new log file. So you might be thinking, oh God, one more remix? So we were remixing the data a lot, and we continue to do it more. We use Go with Glow, which is a distributed computation system similar to Hadoop and MapReduce, to read the new log file and then parse the data again and write it to our database. So in the beginning, we were using a Redis database, which worked well because you can write very specific key spaces. So for example, our customers wanted to view their information by organization. So we have an organization ID, and we have something called a transfer with a start time and the range in which the transfer is active. So as you may know, Redis is a key value store. This is our unique key, and then to get the next set of keys and values, we have the timestamp and a unique ID. UUID, unique user ID. Or universal, anyway. Okay, so then after we get all of our unique IDs, we get the amount of, we do a second key space query with the download bytes, the timestamp, and the bytes downloaded. And then we do another query for the bytes uploaded. Now, at this point, this is only 2 transfers. So as we saw in the previous slide, we have our initial transfer, which was, or our initial query, which was just for the time range, and then the second query, which was for the bytes downloaded for the period, and then the bytes uploaded for the period. So now let's say there is a second transfer. Then we need to repeat the same exact queries. And did anyone catch the name of the files that we're transferring? So I think someone said cat? Yeah? That was the ID. So we still don't have the name of a file. So we need to make another query to our Redis database to get what we call the metadata. So we'll say, okay, the file name is cat, and the user ID is 1. So it was 10cat10 was the unique user ID, and then the name of the file transfer is cat. We're making Rails do a lot of work. Just to get information about one transfer and display it to the user, we're making many database queries. So if our GET request didn't time out, oftentimes the browser would still crash because we were trying to send so much data back that the request would fail. So our tech stack and our implementation was not effective. So let's start at the baseline again. We had massive data generation. How can we get this data from one location to another in a more efficient manner? So before we're using a Ruby script to write it to a log file and then write it to another log file and then upload it to a Rails server, where then it was sent to a Go program to be further processed and write to Redis. Does anyone have any ideas on how we can get our data from our daemon to the next point of data processing? No. So log files are out. I'll give you a hint. It needs to be scalable. And we may stream the data. Kafka. So our daemon can write directly to Kafka, and Kafka can then be received by Spark. So Kafka is a distributed streaming platform. It allows you to write your data in topics. So if we have all information regarding organization, let's say the pink fish, then all information regarding users, the orange fish, and workspaces, the yellow fish. So our data is going directly from the daemon into what are called topics and streamed to what will later be revealed as Spark for further processing. So already on the initial write of the data, we're organizing it in a way that can be understood by the next program. So Kafka also allows parallel processing. Once you get too much data in your current process, you can just create parallel processes of streaming the same data, and things will stay in order. So here we have our fishes have overfilled the streams, and so now we have 2 streams of pink, 2 of orange, and 2 of yellow. So from Kafka, we go to Spark. Spark has a streaming feature. It can receive, stream, and then it can output a stream. So it can receive streaming data from Kafka, process that data, change it a little bit, and then stream it again back to Kafka and make it available for other applications to process. So stream and restream. Here, Kafka has received the stream, it's processed it, and then restreams it back to Kafka, but it looks a little different this time. Okay, the audio is still not working. So yeah, things are starting to look good. We're using Kafka, we're using Spark, and now we have a method of getting the data to our data processing service. So that's using Kafka, and then Spark is able to quickly process the data. And now we are in our database phase. We use Cassandra because it can handle a high amount of writes, and it is very scalable. So in a typical MySQL solution, we may have one table that stores all data around a transfer. What's the organization ID? What's the user ID? But in Cassandra, it's a little different. Since it can handle so many writes, you just create a different table. So here, we have data that is separated by organization, node, user, and workspace. And then we've separated it by uploads and downloads. So now when we make queries to the Cassandra database, we know exactly what table to go to. Instead of sorting through a bunch of extra data, like those ever-growing Redis tables, and then grouping it together, we have all the information in the table. And it gets more detailed than that. So again, this is a real-time streaming application. We have lots and lots of data. And we noticed that we are receiving some latency. So again, we partition the tables by timestamp. So you can make very specific queries based on timestamp and get data back quickly. Now Rails is a little happier. We used Ruby Kafka, Cassandra migrations, CQL, and FactoryBot. Those were some gems that helped us build out these tools. Cassandra migrations is like Rails migrations. You write a script, or you write some details about how you want your database schema to look. You run the migration, and it modifies your database. So there was a problem. Unlike this double platinum hit by Madonna and Justin Timberlake, people did not want to wait 4 minutes to see their data. And that's how long it was taking for our streams to come through. Action Cable wasn't able to process our streaming data quick enough. So we moved to Phoenix and Elixir that was able to process the streams and get it to the front end to make our charts. Here's an example of our logs of our WebSockets and the logs that we have for each transfer. In the end, this is the tech stack that we ended up with. We have a daemon that writes to Kafka based on specific topics. Spark processes that data, rewrites to Kafka, and also writes to Cassandra. Our Elixir app will read from Kafka, create a WebSocket that will be available for our front-end applications. Rails solely is responsible for historical data that's been written and is no longer real time. So we can make specific queries to our Cassandra database, aggregate it, and then send it to the front end without sending too much information in our simple GET request. In the end, this is our analytics platform. We have a chart with streaming real-time data. We have an upload and download rate for all of our current transfers with bytes in and bytes out. These are received from our WebSockets so that we are getting the data as it's received from Kafka. And then for historical data, we can modify the drop-down options at the top of the page. And that will go to our Rails application and hit the Cassandra database. Thank you.